Hello everyone, welcome back to my channel. In the world of FPV flying hobby, or first person view flying, one thing that is interesting to me is the antenna tracker. It's a system that points the FPV antenna of your ground station to your drone and make sure you have a solid video link. As you can see, this is my previous video which features a motion tracker, so it moves physically your antenna and points it consistently at your drone. But what if we could do the same thing without moving the antenna physically? And the answer to that is beamforming or beam steering. In this animated GIF, you could see a series of antennas. They transmit at a different timing, and in fact the delay is cumulative. So this is the antenna that transmits first, followed by this one and the rest. And the end result is the wave will cancel out each other, resulting in a big wave that steers to the left. To achieve this, we need to use phase shifter. However, phase shifters are very expensive, and in this video we are going to explore an affordable way to make our own beamforming antenna tracking system. Here's a fun fact about phase shifter. Phase shifters are found in antennas. If you compare these two antennas here, from the feed point to these two patches, they are equal lengths of transmission lines, so there's no phase shift. However, for circular polarized antenna like this one, the transmission line here is longer than this, and this is to create a phase shift of 90 degrees between the two patches to induce circular polarization. Besides that, the patch has the corners tapered off, as you can see, and this patch itself is already circular polarized as compared to the linear patch with the corners still intact. For our project, we can't use non-adjustable phase shifter, so we can't use fixed transmission lines like this one. To cope with this problem, we have to design our own phase shifter that allows us to vary the transmission lines to delay the transmission to each transmitting or receiving antenna. This is a PCB, which is a 4-way splitter from my previous video, and it works very well. It has good impedance matching. So I use this splitter and work on a phase shifter, which is here. For this project, I had created a 5.8 GHz version of the original phase shifter design found in these white papers here. I'll post a link to it in the video description. Basically, I will have switches in these gaps, and by turning on or off the switches, I could increase the length of the transmission line to the first antenna, second antenna, and so on. So this is the route that we are taking. Basically a poor man's solution to phase shifting. And here we are phase shifting 4 antennas to steer the beam for our antenna tracker. And here's the front view of the board. I've soldered 4 SMA connectors, which are the through-hole mounting types. And I've soldered one more SMA connector here, which is the H-mount SMA connector. This way you could mount your 4 antennas, and then you could connect this to your receiver. Now I have added the RG316 stubs. Basically, there are small pieces of the center core of the RG316 cable, and they are rated at 50 ohms. So I'm using them to close part of the circuit to ensure that the transmission travels the same distance to all the 4 antennas. So basically now there's no delay among the antennas. Okay, right at the center I'm getting about 70% to 72%. Okay, I'm going to walk for my right. Let me see, it's about 22% here at 45 degrees to the right. So at the left hand side now, I'm I'm getting about 22% as well. That was the first test of the field. Now before I head down for the second test, I'm back at my workbench and I have resoldered the joints here, as you can see. The first antenna has a soldered joint here. This is the RG316 stop, 50 ohms each. And here we have 2 of them. And the third one has got 3. And the fourth antenna has got 4. Now with the cumulative delay of 90 degrees from left to right for all 4 antennas, let's take a look at the VSWR. It's doing a scan right now. And it's 1.09. Alright, here I am back at the field for the second test, this time with beam steering. I'm not sure with this delay it's going to steer the beam to left or to the right. So I'm going to find out. I'm getting about 40% right here, which is the right of the antenna array over there. That's the antenna array. I'm getting 40% over here where I'm standing. 57% is about the max I got, and that's basically about 40 degrees to the left of the antenna. Somewhere in between that point where I was standing just now and the center point. Now I'm standing directly in front of the antenna, and the signal I'm getting is about 27%. Right now I'm at the left side and the antenna is over there. And the signal strength here is about 15%. And basically this is the rear view, as you can see. The distance here is the shortest for this antenna and it's slightly longer for the second one. And it's even longer for the third one, and this one here has to travel a full circle. And the end result is quite significant. In the middle there, I'm getting about 27% of signal strength. On the left side, basically the beam is steering to the left. I'm getting 40% there. And here I'm getting a weak signal of 15% right there. So yeah, the phase shifter is working really well. Now it's time to replace these RG316 stops with rear switches so that we could control the switching. For the RF switch, I'm using the F2910 from mouser.com, and this is it. It's really small, as you can see. It's a 2mm by 2mm form factor, and besides my thumb, it looks really tiny. As you can see in this shot, I have soldered 2 magnet wires. These are 0.05mm magnet wires, and the right wire is soldered to the logic control port. The left wire is soldered to the VCC port, which will supply 3.3 volts to the RF switch. Well, it's hard work, but I managed to solder one to the board. This is how it looks like. It's also worth mentioning to you guys that for this project I've gotten myself this 908S 80 watts soldering iron. It has temperature control and a very fine tip. To test the RF switch, I have removed the 3 antennas from the array. They are here, as you can see on the table. So there's only one antenna which is connected to the array. And currently the RF switch is turned off. It's not getting any power from the regulator. Let me zoom in and show you the regulator. This is the VCC line that supplies 3.3 volts to the RF switch. and this other line is the logic control, which is also connected to the 3.3 volts output via the alligator clip. Basically this antenna is as good as not connected. Now let me power on the RF switch by turning on this regulator here. Definitely you could see an improvement. And in this shot you could see there's only one magnet wire that is connecting to the logic port. As long as you feed power to this logic line, the RF switch will turn on. Having said that, I will still be soldering both the VCC and the logic control wires to the F2910. That's because the datasheet states that the VCC has to be turned on before the logic control is turned on, and also all the logic control has to be switched to 0 before switching off the VCC to ensure proper shutdown. Finally, I've soldered the other 15 RF switches, and in total there are 16 RF switches. I had used 4 RG316 stubs over here, 2 of them, and another 2 over here. The reason is because I realized that I could leave these gaps permanently turned on and it would not affect the beam steering permutations. In addition, I had also omitted 8 RF switches at these gaps here. And the reason is I realized that these gaps could be left permanently open and they would not affect the permutations for beam steering in any way. So in total we saved 12 RF switches and a lot of soldering work. As we'll be using an Arduino to control the RF switches, I first work out the various permutations on paper and figure out that 8 Arduino pins are required. Here is the PCB board layout for the logic control system. In this shot you could see the pins of the Arduino fire up to steer the beam to the center and to light up the center LED. And this is an illustration of the signal travel paths for the 4 antennas. Here are the pins fired up for the beam to steer to the left and to light up the left LED. And again, an illustration of the signal travel paths for the 4 antennas to steer the beam to the left. And here are the pins fired up to steer the beam to the right and to light up the right LED. And the same illustration showing the travel paths for the RF signal for the 4 antennas to steer the beam to the right. Alright, this is the PCB board which I came up with for the logic control system. And the brain would be this Pro Micro Arduino, which would be placed right here. And we have ground and VCC. I meant to feed a 3S LiPo pack to the Arduino. However, I realized that if I use a 12.6 volts LiPo pack, the battery will drain slowly in voltage, and that would affect the RSI reading, the received signal strength from the video receiver. So we need a constant voltage, and to do that, I will be using the 7805 5 volts regulator. So the 3S LiPo pack will be fed to this regulator, and the step down 5 volts will then be fed to the Arduino via the USB port here. That's the plan. Initially, I plan to power all the RF switches separately using this regulator. This is a 3.3 volts regulator. The code name is 17-33G. So I designed a heatsink here to cool off the regulator. But I will not be using this anymore because this is a 3.3 volts Arduino, which means that the pins out will give 3.3 volts, and I could use the individual pin to directly power the F2910 RF switches as well as the logic control at the same time. Alright, I've soldered the components for the logic control board. As you can see, it now has the connector for the 3S LiPo pack as well as the connector for the RSSI in. So we could use this connector to connect to the RSSI or receive signal strength from the video receiver, and that voltage will be read by the Arduino. And here basically these VCC and ground wires are connected to the 7805 regulator at the back here. The 5 volts out goes to this USB micro connector, and the USB micro connector will power the Arduino. And because I'm only using the 5 volts, I do not want the 12.6 volts from the 3S LiPo pack to go to the Arduino. I will not be soldering this VCC trace here. There's no pin, as you can see. There's no pin to the Arduino, but there's a pin here for ground. I've also soldered the other pins required to hook up all the traces to the Arduino board, like so. So you just have to line up all the copper wires, and we have the Arduino board in place, and I could now solder all the legs. And I talk about the LEDs. These are the LEDs that I've used. They are standard LED lights, and basically I just added resistor at the back, pull up resistor to ground to prevent overcurrent to the Pro Micro Arduino. And that's it. The next step is to connect the RF switches to these points here. These are individual points, and it's really easy to recognize them because they are in the same position as the other board. So, and there are holes, so I could insert the magnet wires through these holes from the back, and once the ends come out, I could solder them to the traces, and the circuit will take care of the various permutations, and then we will use the codes to control the beam steering, and the LED light relay is to indicate which way the antenna is steering, because we can't see the radio waves. Alright, here's the completed products. I have all the magnet wires soldered to the logic control board. From the side view you could see them, and I've checked for continuity. There's no problems with the soldering. Now it's time to load the codes. Here I have a 3D printed enclosure to protect the electronics, and the main boards were secured via the 4 black screws here, which are plastic, and at the back is a clear plastic sheet. I have the PLA part if you like to 3D print it, and I'll post a link to the STL files for printing, the enclosure and the backlit cover. Here I'm uploading the codes. It will steer the resultant beam of the 4 antennas, so that the beam will steer to the left, center and right. And for each direction, it actually records the RSI. After that, it will compare all 3 RSI and figure out which direction has the highest RSI, and then it will steer the beam to that direction. And it does so very quickly in less than a second. Alright, I have the beam steering antenna hooked up to this Quantum video receiver here. This video receiver has a built-in RSI out, so it's really convenient. I can use the RSI cable from the logic control board here and plug this jack right into the port here, like so. And I'm using the monitor so that we could see what's going on through the testing. Now we are going to power up the monitor and the VRX using this 3S LiPo pack. And lastly, we'll turn on the beam steering antenna using the balance charging tab of the LiPo pack here. And it's turned on. You can see the light. Currently it's doing scanning. There's no signal, so it's jumping around. And the Arduino is turned on. You can see the light here. Alright, it's time to test whether the beam steering antenna actually works. Here's my test setup. At the window I have the VTX. It's a 200 mini watts VTX, and I have the camera looking at this globe. And now I'm going to step outside of the house. Now I'm standing outside the door and I'm focusing on the 3 LEDs to see where the beam is going. Now the beam is going right, back to center again, and now it's steering right, which makes sense because I'm turning left. Now it's doing something strange. It's picking up a signal from the left and steering the beam left. Okay, yeah, centered the beam back to center. And now it's steering the beam to the left, which makes sense because I'm turning right. And now it's picking up a signal from the right. Okay, now it's back to center beam. Yeah, it's doing the strange thing, picking up a signal from the left again. Okay, back to center beam. Okay, it should steer the beam to the left really by now. Yep. Well, that was a quick test of my beam steering antenna. It works pretty well and I'm happy with the results. For the actual testing using a drone, I have to wait till this pandemic is over, as it's locked down now and we are not allowed to fly RC outside. The next step for me is to tune the code so that it works better. As you can see here, there's a delay value of 100 and this sets the check for need to steer the beam at every 0.1 seconds. A lower value will basically increase the aggressiveness and we'll be scanning like almost the entire time. And a higher value will make it scan at a longer interval period. So we need to find a sweet spot so that it doesn't scan unnecessarily. And talking about that, we have this if statement here. So it only starts to steer the beam for scanning when the RSI falls below this threshold of 0.85. I did several tests on the Quantum V RX. Basically at 0.76 volts, I know the color video will be 50% snow. And at 0.7 volts RSI is black and white video. So now I have it at 0.85, which is pretty grainy and not so good video. So by changing this value, you could actually fine-tune whenever there's a need to scan again. Because as it's doing the scanning, sweeping from left to right, the beam could steer away from your drone and we don't want that to happen unnecessarily. So really it's getting the sweet spot between the delay value and this threshold. I apologize for this long video. I hope you have stayed all the way to the end here. As that's all I have for this video. I hope you enjoy it and thank you for watching. See you again.